sorry, I was on mute. Yes, let me just share screen. What can people see right now? Can you see?
Oops. I can see those.
Spoiling everything. Okay, cool. You can see slides now?
Yes.
Great. Okay, so I think we've sort of met all of you a little bit over the last couple of days, which has been great. But Kiva and I are going to lead the morning sessions for the next few days. So Kiva and I together have created an initiative called Mathematicals, which we mentioned a little bit on the first day. And we'll talk a little bit more about that. But our plan for these days, really today, we want to just give some examples of mathematical modeling and really more physical mathematical models, because I guess the specific one you're doing is a really interesting model, but it's more, there's lots of room for creativity in making that model, as it's not really something that's set by physical laws. You can decide how you want to give benefit to these different plants in order to order them for the conservation efforts, whereas the modeling that we're familiar with is more physical modeling. So we're going to talk about some of those and give some examples. And then tomorrow, we want to talk a little bit more about mathematics outreach, which we're very passionate about, and how to create some sort of fun videos to give bite-sized introduction to different mathematical topics. So we'll talk about that more tomorrow. And then I think Friday, the focus is really going to be presenting the projects, but we'll see how everything goes before then.
Okay. Yes, and then just kind of touching more on what Jess said about the different models we're going to introduce, we're hoping for this to be as collaborative as possible. So at any point, if you have a question, either just interrupt us, there's no problem, just turn on your microphone and ask a question, or put it in the chat. If Jess is talking, I'm going to be keeping a close eye on the chat for any questions for her, and likewise for me. So don't be shy, and there'll be some opportunity for questions and discussion as well. So quickly to reintroduce ourselves, we're from where we founded this Mathematicals outreach initiative, which is really aimed at encouraging underrepresented minorities in the physical sciences. So we have experienced being one of few women in our classes, growing up being one of the few girls in our classes, and we know that this extends throughout different minorities and cultures and things. So we're trying to be as inclusive and as representative an organization as possible to showcase and encourage as many different types of people into the physical sciences, in particular maths. And we really love trying to communicate how fun maths is and how it can be accessible. A lot of the time what you learn in school and what you learn throughout your education can be quite boring, and you can't really see how it's going to be useful in real life. So we're hopefully going to show you some of the really cool applications that we've worked on and that our colleagues have worked on, that's all based upon the mathematical principles, which you clearly understand so well from working with you all these past couple of days.
So we just wanted to have one slide each on ourselves. So I'm from England originally. I was born in the UK, but I actually grew up mostly in Southern California. I did my undergraduate degree at UCLA, and then I returned back to the UK to do my master's and PhD in Oxford, which is how I met Kiva. And I'm now working in conjunction with both MIT and Brigham and Women's Hospital. So I'm living in Boston at the moment. And as I mentioned briefly on the first day, I'm working to help understand cardiac diseases. So I'm using sort of geometric principles, and also modeling of fluid flows is a big thing about what I did in my PhD and what I'm doing now. And I gave a fun fact about myself. I'm really passionate about great apes, and Jane Goodall is absolutely my hero.
And I'm Kiva. It does not look like Kiva. I put in my little name on Zoom, how you actually pronounce it, if anyone actually wants to ask me a question. And I'm from Ireland, which is hence the funny spelling of my name. And as Jess said, met in Oxford doing my PhD there with her. And now I'm working for NASA, looking at planets outside of our solar system. So planets that are really far away, trying to understand what they could be made of. But I'm not in NASA at the minute because of the travel restrictions and COVID. So I'm actually in Ireland, and that's why you all have to get up at 8 a.m. because the time zones mean that I'm a lot further ahead in the day than you. And my fun fact is that I'm currently applying to be an astronaut. So wish me luck.
So we wanted to use a feature called Slido. I don't know if you've all used it before, but we just wanted to open this up for a sort of general discussion by asking you, what do you think maths can be used for? Please throw out anything. And so if you go to slido.com, maybe on your phones, if you have phones where you can do that, that might be the easiest way. And it's going to prompt you to enter a code, and you'll want to enter OMC_maths. Another thing to mention, Kiva and I are going to say maths a lot instead of math, just because.
Sorry, this is not, oops. Okay, yeah, 2 seconds. Something strange happened with our Slido there, and I'm just going to fix it. But Jess, yeah, keep talking. Yeah,
I was just going to say that Kiva and I will say maths a lot instead of math, just because in the UK it's abbreviated to maths with an S, which I never know why there's that difference. It's always a bit confusing. Sorry, bear with me. So it's nothing, maybe nothing's coming up on your Slido just now, but give it a wee second and hopefully something will appear. Okay, let me reshare my screen. So on your Slidos, you should see a poll now, do you? I think I see it. So we can type. See a poll.
Your presentation is not sharing, I think.
Is it sharing now?
Yes.
Yeah. Okay, cool. Cool. Okay, so then hopefully now on your Slido, you should have a poll that says, what do you think maths can be used for? And if you just type in, you can type in as many answers as you want. Let's just start getting a bit of an idea of what you guys think maths is useful for. Maybe what you've used it for in the past, or maybe that you just think you might be able to use it for that. Yeah, or what you'd like to use it for. Finances, great one. That was actually what a lot of the people in my undergraduate classes would have gone into finance. To model absolutely anything, dimensions, astronomy, excellent. Finding dimensions, astronomy for medicine, yeah.
Quantitative finance.
Quantitative finance, excellent. Yep, there's medicine. Describing the world. Card games is really good too, because there's lots of probability you can work out with cards and how likely it is to shuffle, because I think it's extremely unlikely to have any particular, I can't remember the exact probability, right, but you've probably heard that before, to have any particular layout of all the cards once you shuffle is extremely unlikely. There's arts, which is very good, because that's something that you might not usually associate with maths or with the physical sciences. Music particularly is very, that's an excellent one. Yeah, mathematically driven. Very closely linked. Computer science, definitely. Analyzing data. Cooking, I like cooking because I do that all the time if I'm cooking, and especially if I'm converting between UK recipes and I only have US instruments on hand. I'm having to convert all the different units. Architecture, that's a very good one. There's a lot of maths in architecture. Physics is there. I think we missed calling out that one. Physics and chemistry, absolutely. Describing the world, definitely. And the computer science, the graphics aspect, that's a really good point, because that's something that you often see, the advertisements for jobs, and they'll be calling for a mathematician or somebody with some analytical background. Okay, excellent. Those are all really good examples. So now we're going to hopefully ask you another poll. So this next question is, what do you like most about maths? So why do you do it? Why are you here at 8 a.m. on a Wednesday? And hopefully your poll should refresh and you can start putting in some new answers. The challenge, excellent, love that.
What was the code for the poll?
I think if you just refresh, sorry.
If you refresh, it should work, or just type in OMC_maths. Again, it should be hopefully the same code. Okay, this is a good one. I love how there's more than one way to get to the same answer. So you don't, I always like that in school, that I didn't, with other subjects, I felt like I had to memorize a ton of information or learn a particular way to do things, whereas maths, you could think about it in so many different ways. And I think that's what we'll talk a little bit when we talk about outreach tomorrow, but I think that's one of the important things is
hearing the same concept in lots of different ways, because I think that can really, and be able to explain it in lots of different ways too.
Yeah. Okay, always something to learn and everything is interesting. Great. Creativity, excellent. I love solving equations and formulas. Very good. Puzzles is a good one. They are just sort of like more formal types of puzzles. That's what your plant model is, essentially a puzzle. How can you allocate costs in the most efficient manner?
Helps me think logically. I like that too, because I do think learning maths just does help you think in other situations too.
And I like this one. I like how it is abstract, but it can be applied to everything. And that's going to be a real key in when we talk about outreach, how you can translate this abstract concept that is not going to be obvious to your audience, might be obvious to you, but the general public aren't going to understand all these complex maths that you get, and how you can communicate that in a straightforward way.
It pays well. That's a great one.
It is.
There's lots of jobs with maths that can pay well.
God, you are coming up with great examples here. I can hardly keep up. Math is correlated to many other things, which is why I like it. Love that.
I love how you can apply a single concept to so many things in many ways. I think that's really cool too. But yeah, because sometimes, especially working out probability in a certain situation, then you can apply that to a different situation, but it's the exact same calculation.
And that's actually why my career trajectory has been so back and forth, because in my PhD, I was doing something entirely different to what I'm doing now. So people might look at that and think that I've changed jobs essentially and completely jump shift, but actually it's just because maths is so versatile that you can start applying it in any different field or discipline that you might be interested in. Okay, great. So let's move on to talk a bit about some of the models that we've worked on.
So I'm going to start this. We're going to talk about four different models, 4 different projects really that people in Oxford actually worked on. So I'm going to start by talking a little bit about what my PhD was on. In the PhD program that we did, every single project was sponsored by an industry sponsor. So some sort of company came to Oxford and presented a problem that they think mathematicians would be able to help solve. And the company that my PhD was sponsored by is a company called Boston Scientific Corporation, and they manufacture medical devices. And a specific medical device that they manufactured is called a ureteroscope. So this diagram has lots of words in it, but really, if you focus on that thing that Kiva's sort of outlining with her mouse, where you've got that white handle there, and then there's like a long, thin shaft. So it's a procedure used to help remove kidney stones from the body. So it's a little bit of an uncomfortable procedure. So maybe I won't talk about the details too much, but you can imagine probably how this is performed. Essentially, the surgeon holds this device, it's inserted into the patient, and then that long tube goes up into the patient's kidney, and that's where the kidney stones are. And the thing that's really cool about this is there's a tiny microscopic camera at the end of that scope, and that camera basically provides an image of inside the kidney. And then the surgeon, when they're performing this procedure, they're looking at a screen, and that's showing the stone inside the kidney. So I think I inserted a short video. I don't know if that will play.
Oh, no. I don't think you've granted me. Oh, I have to sign in. Damn it.
Okay, that's
Okay.
it's.
Oh, sugar.
That's okay.
Sorry.
It's just I can find it actually. Maybe in the break I'll show it to you later. But it's essentially just a video that's from that camera that that I have access to. But essentially, where the mathematical modeling came in is, for this procedure to happen, there's a saline bag that's hung above the patient. So it's filled with a sort of light salt solution that can go into the body. And that saline solution flows, it's sitting in a bag that's held above the patient, and it flows under gravity through a tube. It goes through the scope, and there's a thin hollow channel in the scope that it flows through, and it goes into the patient's kidney. And that fluid's really important for this procedure because it washes away all the stone dust that's building up. The surgeon is essentially using laser fibers and other things to break these stones apart. And so that fluid washes the stone dust away. And so really what they need is, for this procedure to be successful, they need to get quite a lot of fluid into that kidney to be able to properly wash away all this stone dust. But it's really important that the pressure in the kidney stays low. So that was really where the mathematical modeling came in, is I wanted to make sure that there was enough fluid getting into the kidney for the patient to be able to see, but the pressure in the kidney wasn't going too high. So, and then another thing to mention is, in the same channel that the fluid was flowing through, the surgeon would pass things that they called these surgical tools, which were essentially long, thin rods. And some of these were laser fibers that we used to break the stone apart. And so if you look at the picture on the right, I have that part where I say inflow. So if you're thinking about looking at a cross section of this tube, the fluid was flowing through, and then there was a solid rod in the middle. So I wanted to think about how we could help redesign that scope to make sure we get a lot of flow into the kidney, but the pressure stays low. So if you click to the next slide, then as I mentioned, the problem was, how do we design the scope for the most efficient surgery? So I just wanted to ask, Kiva, I can't remember, were we just going to do this as an open discussion for people to shout things out? We weren't going to use Slido, right? Yeah. If anyone, maybe you can type in the chat or say it out loud. What do you think would be some assumptions we might have to make in order to model this? Does anyone have any thoughts on what just anything that we might need to assume to be able to model this fluid process? Size of scope, brilliant, perfect. Yep, exactly, that's really important. And actually that is something that was sort of fixed, is they, as you can kind of imagine, because this is having to be inserted into the patient, there's only kind of a maximum size that they can use. So I'll probably mention next what the assumptions are. And then the other thing I wanted to ask is, could anyone think about what the variables might be? So variables in the models, as Wesley's mentioned, they're usually things that we're trying to solve for.
Size of the kidneys.
Size of that, yeah. So that might end up being an assumption more, the size. I guess depending exactly how we're defining these, I would think of that maybe more as an assumption. We might assume a size for the kidney. Kidney stone size is something we'll have to take into account too if we're wanting to model the breakup. So
also whether they have one kidney or two kidneys.
That is very true, actually. Yeah, I'm sure, because I know, yeah, people can have one kidney removed, can't they? Saline solution, great point. And that actually is what's going to be really important, is the properties of this saline solution. Because we're modeling the flow of that saline solution through the scope and into the kidney. So this is what I just wrote down. So the assumptions we make is that the flow of the fluid obeys some simple physical laws. And that's kind of a theme Keeper and I are going to talk about a lot with physical mathematical modeling. And these laws are usually derived from things you've seen before, sort of Newton's laws, like force is equal to mass times acceleration, or conservation of momentum, or some of those things you've probably seen before in your physics classes. You'll usually use those principles to derive some equations. So that's, and we do that the same with the fluid. It ends up just being a conservation of mass and a conservation of momentum, and you use those to derive a set of equations. Something else I assumed is that the scope stays in one place during the surgery, just because I wanted to model fluid as basically flowing through a long straight tube. And that kind of was a big assumption, because really actually this scope is quite flexible. And so it's moving around parts of the body, and the surgeon's able to move it around to find the stones. But that was an assumption we made to kind of simplify the modeling process. And what I defined as the variables were the flow rate. So how much fluid is going to flow from this bag through the scope, and what is the resulting pressure in the kidney. And another variable, I was looking at how changing the shape of the scope channel and say the length of the scope, how that would change the flow rate and the pressure in the kidney.
What about, this might be more of an assumption, but the viscosity of the fluid that you are using?
That's exactly right. That's such a good point. And that comes up actually in the physical laws that we mentioned when we're doing a sort of a force balance. There's a force that comes from the fluid viscosity. So for people who haven't heard viscosity before, it's basically how sticky a fluid is. So if you think about honey, that's going to have a very high viscosity. It's very sticky. But something like water or saline solution, the viscosity is going to be lower. But great point, Patrick. That comes up exactly in these equations. So I think, oh yeah, then this, so when I was thinking about modeling the shape of the channel, thought about looking at a single cross section. So you can imagine this is that channel I mentioned in the scope, and there was that solid rod inside the channel, which is the surgical tool. It's usually a laser fiber that they use to break up the stone. So often when we do mathematical modeling, we take a system that might seem quite complex, and then we represent it as sort of simple geometrical shapes. Like this, it's basically a cylinder it's a hollow cylinder with a filled cylinder inside. And so then if you think about taking a slice along that tube and sort of rotating it, you're essentially looking at a circle with a solid circle inside. And so this is the sort of different shapes I was thinking about. So if you imagine that cross section, instead of having a circular cylinder, you could have a cylinder that has an ellipse as its cross section. And you could keep the same size. So you could keep the same total cross-sectional area, but you just change from a circle to an ellipse. And a lot of my PhD was, or part of my PhD at least, was thinking about what happens if we try out all of these different geometries. If we think about having the channel of the scope circular, if we think about having the cross-section of the tool, the channel of the scope, if we think about having it elliptical instead of circular, if we think about having the cross-section of the tool elliptical, and what about if we move the position of the tool in the channel? What if it's not in the center? So I thought about all of these different questions, and then I think I've just got one plot here that it turned out actually this was the best cross-sectional shape. So for the sizes that they wanted for the scope, this elliptical cross-section, and then this black area is the cross-section where the tool is. Those ended up being the best shapes for the channel in the tool, and it meant that you got the highest flow rate and the lowest pressure in the kidney. And so this plot on the right is actually just showing the different shapes and what happens to the pressure in the kidney over time. And you can see that the red one, which is the shape we determined to be the best, has a lower final kidney pressure. And what was quite exciting for me is the company was really interested in this, and they actually patented the design. So I have my name listed as an inventor on a US patent, which was really exciting, especially for a mathematician. I didn't expect to have that as an outcome. So it's a long patent process for them to actually, so they haven't actually manufactured this device. I don't know if they actually will, but I guess theoretically, if they do make it and they start using it, I don't know what that means, but yeah, maybe I get something that would be exciting. Okay, so I think that was it on. Does anyone have any questions on that project? It was a lot of sort of introduction to a surgery you might not be familiar with, and then modeling fluid flows. But feel free to ask me afterwards or in the chat if you do.
Okay, so we'll talk now a bit about something completely different, which is how you can use maths to help you make a smoothie. So this was a short project. I only worked on this for 10 weeks during the summer of my first year as a PhD student. And it was like Jess's, it was in collaboration with a company. It was with Shark Ninja. So this blender you see on the left is the blender that we were studying, and I was given one to look at. And the goal of the problem was, how do we make our smoothie as smooth as possible, but minimizing things like noise and the energy usage. So you could, if you had unlimited noise capacity or energy capacity, you could make that blade spin as fast as you want, and it could be as difficult. You could require all the torque to spin it and it would chop everything, but that's not realistic. So there's boundaries set by the company that they wanted to try and get a really smooth smoothie, but they didn't want to have to put a ton of energy in, which was going to cause a lot of extra noise and use a lot of electricity. So this picture in the middle is the blade that I was studying. So it was sort of consisted of these 4 wing-shaped blades. You can't see the other one off the other side of the picture, but these 4 sort of angular blades. And there's these kind of funny blade things in the middle that I didn't worry about too much, but this was the anatomy of the blade. And they generated some data. So they had made a smoothie, and after blending it for a certain length of time, they used like some fancy laser stuff to try and measure the radius or the diameter of the particles in the smoothie. And this was the final distribution that they got. So they were pretty happy with that. They were happy with how smooth it was, but they didn't like how noisy their blender was. And they wanted to try and get the same distribution or better with less noise and potentially less energy. So to break that down into a modeling problem, our goal was to produce the finest puree in the most efficient manner. And that involved trying to understand which operating parameters would govern the size distribution. So by operating parameters, I mean the speed of the blade, the angle of the blade, or the length of the blade. There was different things that we could think about in terms of the cup, the blending vessel, in terms of how it was designed. If it had there'd have these ridges down the side of it, and those ridges would kind of help trap bigger particles and push them down into the blade. But that was sort of the first step, was trying to understand all these different things. The next thing was to modify the parameters to minimize the particle size. So now, once we figured out which parameters were the most important, how could we modify them to get the smallest particle size possible? So not too different from when you're thinking about your plant model. You're thinking about how can you order them based on this feasibility, based on this benefit. You're trying to think about how these parameters play in together to give you the best ranking. This same sort of thing. You're trying to think how these parameters interact with each other to give you the smallest particle sizes. And then the final step was to advise the company, to come back to them and say, this is what we think you should do to get a good particle size distribution at a lower operating speed. So that was our goal. So let's, in the same way we did with Jess's model, do you guys have any idea what you think different assumptions or variables might be for this model?
The blade length is a variable. The types of fruits that you're going to be, like like whether it's fibrous or whether it's mostly water.
Yeah, so kind of how easy it would be to chop.
Yeah.
Yeah, very good. And Isabella said time of blending is an assumption. Actually, I think time of blending is a variable, because we want to say if we blend it for 5 seconds, this is our distribution. But if we blended it for another 5 seconds, it would be a slightly different distribution. But that was a very important part of the model, because the longer you blend for, the more noise you're getting as well. How much fruit we use, excellent, yeah. So sort of tying back into what Patrick said, if you had all fruit and no liquid, you might not get very much circulation of the fruit. So you might not get any sort of chopping. Whereas if you have a bit less fruit, a bit more liquid, you'd get a lot more movement within the container. So that's a very good point. Thinking back to what Jess said about her assumptions, can you think of one that might be relevant here too? She mentioned something about, when she was talking about viscosity, that all sort of tied into something.
The just like ability for the fluid to be moved around,
Yeah.
and how the blades are going to interact with the fluid on a almost like how the fluid is going to move around, because if it's all going to stay at the top, then there's no point. And if it's all going to come down to the bottom, that's the optimal decision. So you want something that is not only going to spin really fast and optimize for that, but it's also going to move as much.
Move things. Yeah, exactly. So Jess mentioned with her model, there were some simple physical laws that she was going to make sure that the fluid obeyed in the same sort of way. So just like Patrick was saying, how is the fluid going to move around? Our fluid is also going to follow some simple laws in terms of viscosity and rotation and things. But then another point that Patrick made that was very good was how the blade interacts with the fruit. So let me just bring up some of the assumptions and variables that I used. And I'm just going to jump down to this bottom assumption for a second, that we assume that one piece is chopped in two. Okay, so if a blade hits a piece of fruit, we're assuming it just splits in two, not into many pieces, one into two. So going back up to the top, we're saying that the mixture is well mixed. So this is quite similar to Sharanya's point about how much fruit we use. We want to make sure that there's an even distribution of particles, fruit particles throughout the whole mixture. We're not going to say there's a big clump of fruit down the bottom and no fruit at the top. We assume that the food particles get chopped by the blade. So if a blade comes near, if it touches a piece of food, that food gets chopped. It doesn't slip past or something like that. We assume that the food is randomly and continuously chopped. So there's always chopping taking place. So sort of back to what Patrick said, you don't have loads of stuff at the bottom not getting chopped. Everything's sort of happening randomly and continuously.
I would think that one piece getting chopped into two would have to be something that you would not necessarily a variable, but something that you'd have to a constant that you'd have to optimize for, because if it's a really thick blade and you're dealing with particles that are in the micrometers or whatever, then you're not really gonna get any chopping at all. It's more just going to be pushing it out of the way.
Yeah.
And then at that point, it's even if you do it for another hour, it doesn't matter.
Well, that point that you just made was actually, I'm not even going to talk about that in this short introduction, but that was one of the things we found. If I just quickly jump back to their picture, you see this little peak for really, really small particles. That was really difficult to reproduce mathematically, because that was basically saying, as Patrick did, that there's sort of a limit. There's a size particle that doesn't no longer get chopped. And those little tiny particles were missing the blade, or they would come up to the blade and they would sort of sweep over it or sweep under it. And that was sort of the limit of how small the particles could be chopped. And to try and capture that peak required a lot of fluid dynamics and something called Stokes flow and things about the blade. So so yes, this assumption that I'm making that it's chopped in two is a big assumption, and it's a first assumption that you would make. And then once you look at your model and you say, actually, that's not such a great assumption because it's not helping me capture this peak that's evident in the data. So then you would go back and start to add in a bit more complexity and try and build upon that. So that's a very good point. And then quickly running through these variables, the initial size of fruit pieces is important because we have to have a sort of initial distribution that we then blend and we see how it evolves. Speed of the blade, I think that was said. Shape of the blade, Patrick mentioned the length of the blades and things, that's important. And the blending time is very important too. So I'll quickly go through the simplest model. So, okay, this is a disclaimer, this is not physical, but this is how we would start a modeling process when you've got something as sophisticated as this blender with all the fluid dynamics and all the particles. You have to start somewhere very simple. So we're going to start with a one-dimensional model. So I'm using a caret, but really we're thinking of this as a long one-dimensional line, okay? So if you have a long dimensional line, we're going to first of all think of this in terms of this line being made up of n tiny pieces. So if the line is of length L, and then there are n tiny pieces making up this long line, then each little piece is of size L divided by n, okay? And n is huge here. We're talking about like really, really big. So then those little pieces are really, really small, if you know what I mean. But we have to have some sort of discretized understanding of what we're doing. So we've got one long piece, lots of little tiny pieces. So when a piece of length L is chopped, and remember our assumption was it's getting chopped into two pieces, then one of those pieces, so let's say this one, is going to be of length J times L over N. So that means there's J pieces. And the other one must be of length N minus J L over N. So it's made up of N minus J pieces. So you can see when you add those two back together, you get back to your long piece. So that was how we started the model, as simple as that, how we started thinking about it. And then effectively, the whole model was based on tracking the number of particles of each size. So this is obviously not a very good equation because there's no real numbers or symbols. We're using it in words, but bear with me. So after every chop, we look at the number of particles of size n. And the way we figure out what that number could be is that we look at the number of particles of size n before the chop. So we have that initial number. We subtract off the particles that were chopped to smaller sizes, because some of them will be hit by the blade and will suddenly be smaller, so they're gone. But then we also add on the bigger particles that have been chopped and ended up as size n. You understand? So you're sort of got this, you're losing some particles due to being chopped, but you're gaining particles that have been chopped from bigger sizes. And that was effectively the basis of this model. And what you could do from this was you could start to track the model size, the particle sizes over time. And the way we worked out the number of bigger particles that were being chopped is we started to introduce something called a likelihood, a chopping likelihood. So the likelihood that a particle was going to be chopped, and that depended on how many particles of that size there were, because if there was loads of those particles, then the likelihood that one of them would be chopped was quite likely. And the model that we did, so it's sort of similar to Jess, I'm sorry, this is moving on after this, similar to Jess, the outcome of this project was that we were able to design a new blade or advise them about how we think they should adapt their blade. And although it was not patented, it was observed to perform better than their initial distribution. So something as simple as this, right, that was derived from just thinking about a straight line being chopped into little pieces, was actually able to give this company enough evidence and enough physical intuition to design a new blade that was actually a better model than what they were currently using. Does anyone have any questions on that? It didn't actually show any equations that actually probably would have helped you all out a bit more, but.
How did you know that you had to add the bigger particles, the last part of the model, the equation? I see the first two, but how did you come up with, decide, or?
So that was just, so this is assuming, so this n that I'm assuming here is any n smaller than the biggest particle in the distribution. So if you started with particles of size big N, then this term wouldn't exist, right? Because there couldn't have been any particles bigger than n to possibly be chopped down and become size n. So this is sort of a more general equation for a particle of a particular size n. If there's any particles that were bigger, so say there was a particle that was size 2n, then if it was hit by the blade and was magically chopped perfectly in half, then that particle would become, you get two new particles of size big N. So you'd have to add those on to the number of particles that you're considering. Does that sort of make sense?
Mm-hmm.
And I just wanted to add to this that Kiva got to keep her blender too, which I think may have not got a patent, but she got that blender and it was a good blender.
I did. That was one of the perks, and it still works to this day, although it's a bit temperamental.
It is loud too, so I think that was definitely,
but this is the thing. Yeah, it was really loud. So when they described the project to me at the start, I thought, yeah, blenders can be loud, but this blender was really loud. So they really did want to try and fix this problem. So if you ever get a Shark Ninja blender, you can send me a picture of the blade and I'll let you know if they've stolen my design without my patent. Okay, so we'll move on now to cereals.
Yes, so this was a project actually that neither Kiva or I worked on, but a colleague of ours worked on, and we just thought it was so cool. It was sponsored actually by Nestle, so Nestle, who make a lot of the breakfast cereals, and something else that was exciting about doing these projects is we often got to go and visit the companies too, and Nestle they're based in Switzerland, so our colleague Michael, who worked on this project, got to go and visit Switzerland for quite a few weeks every year, which was great. So the way that they often make cereals is they extrude them. Essentially, they have these extruder machines, and they put a sort of wet mass of, so sort of imagine if you got Cheerios and you made them all wet and smushed them all together into a gooey substance. That's what goes into the the top of that extruder, and then essentially they'll extrude out a long, thin column of that wet material, and it will then be chopped off and it will dry and harden into a cereal shape. So the thing that's really important here is the shape of, they call it the die, and it's essentially the opening of the extruder. So if you look at that picture on the right, there are, so I meant the die shapes to be pointing at those metal circles at the bottom. You can see, so on the far left, those are the circles, and those would extrude out sort of circular shapes. And the thing that's complicated about this, though, is the die shape you get isn't the cereal shape you end up getting, because this cereal, once it comes through the extruder, it actually continues to expand once it hits the air. So if it didn't, then it would be very simple. You just want a die shape that was the same as the shape of the cereal that you wanted overall. But the complicated thing is, because it expands after it comes out of the die, they needed to use mathematical modeling to figure out how the cereal, the wet cereal, would expand after it left the die, and to work out what shapes it would create as a function of the shape of the die on the extruder. So again, so sort of defining the problem, it was really what breakfast cereal shapes are possible to make for particular die shapes. So again, if anyone has any thoughts on what assumptions or variables might be in this model, feel free to throw them out or put them in the chat.
I think that'd be so complex that the only like practical way of going about it would just be to design a physics simulation for the problem in the computer and then graph the data there.
That's a really great point that you bring up, is that often, so the mathematical models Kiva and I talked about before were ones that we could actually reduce to equations that we could solve by hand. But often the physics is so complex, exactly as you said, Patrick, that it ends up being something that only a computer can solve. And actually, our colleague Michael, who worked on this, was able to come up with some slightly simpler models, which I'll mention. Let me just see the chat as well. Exactly, Sharanya, what the cereal is made of and its properties, that's really important. And that's playing into the physical equations, as you said, Patrick, that are going to end up being solved. Exactly, Isabella, the consistency of the cereal mixture, that's totally right. So we need to basically know what that cereal mixture is made of and how it interacts with the air after it leaves the die. And just to mention actually what so yeah, Kiva, if you want to put up the assumptions and variables, thank you. So yeah, we assume that cereal is extruded as a wet substance from a tube, and exactly as you've all said, we need to assume that this wet cereal obeys some physical laws. And the physical law that this actually obeys, it's different from say the saline solution I was looking at first, because with saline solution, so with water, you often say that water is incompressible. So essentially that means that you're not going to be able to change its volume. You can't sort of take water that's in a big tub and try and squish it down into a smaller tub. That's just not going to work. But actually this mixture that they use to make the cereal is called compressible. So it means you can smush it down to a smaller size. So you can sort of think of a sponge. You could take that sponge and you could squish that sponge smaller. And even though that's not a liquid, it's the same concept. That sponge is compressible, whereas something like water is incompressible. So that's actually a big physical factor that comes into making these equations, because if you have something that's incompressible, then your volume is going to stay the same, whereas if it's not, then your volume can change as a function of how much force you put on it. And the variables they were interested in changing was the speed of the cereal extrusion, so how quickly it shoots out of that die, and then importantly, the shape of the extruder, or actually the shape of the die. And so this was, so I think these are GIFs. I'm not sure if they're going to play.
Hang on, I'm going to play them from the other way, just like a regular Prism.
Oh yeah,
this Slido thing is ruining everything.
Okay. Yeah, so you can see it. So just for fun, our colleague Michael, who worked on this, decided to see what would happen if you started with a Mickey Mouse shape. So you imagine your die is a Mickey Mouse shape, and then this is imagining the sort of column of wet cereal that extrudes out of that Mickey Mouse die shape. And you can see on the left, it's showing the cross section as it evolves over time. And on the right, it's showing that cross section evolving as it shoots out. And you can see that it goes from a nice Mickey Mouse shape as it leaves the die and becomes almost circular by the time it gets to a point where they chop it off. So that would be a forward model, is you would basically provide a shape for the die and the model would be able to tell you what would be the resulting shape of the cereal. But really, the thing that's quite complex here is what Michael needed to figure out was he knew what cereal shapes he wanted, or at least Nestle knew what cereal shapes they wanted to make, like maybe some of these complex shapes on the right. But the question was, what shape die or what shape opening for that extruded cereal to come out is needed so that it reaches that cereal shape by the time they chop it off and it hardens. So that's quite and that's actually something called an inverse model that you might see. Is you basically, you know what outcome you want, and you need to figure out what you want to start with so that your model will give you that outcome. So that was quite a sort of interesting aspect of this project, I think. Does anyone have any sort of cereal related questions on this?
The granular properties of of the mixture, because even though it's compressible, grain absorbs air differently based on the content of it. So if it's going to absorb a lot of air, or if it condenses on the surface, which is going to prevent it from absorbing air until the very end when it's exposed, or something like that, little inconsistencies in the mixture could create other variables.
Definitely, yep. And that's a really good point, that it's not just going to be dependent on the die shape, right? It's also dependent on what type of cereal they're making. If it's Cheerios or Cocoa Pops, they're probably different, sort of different consistency mixtures.
Okay, and then the last model, excuse me, that we'll talk about is actually what I'm currently working on, which is how we can use maths to understand what planets are made of. And the way we can do that, so I don't have, let me just leave that for a second. These planets are really, really far away, okay? That kind of goes without saying. The closest, they're called exoplanets. So an exoplanet is a planet outside of our solar system. And the closest exoplanet is more than 4 light years away. So that's millions of miles, because it's the distance that light would travel in 4 years. So we can't send anything there. We can't go there and kind of poke around and say, what are you made of? Take little samples of the atmosphere and try and figure it out. So the way that we try to understand what these planets are made of is we look at the light being reflected off them. So most of these planets are orbiting around a star, just like we are, but a different star. And as they orbit around the star, they pass in front of their star. It'll block some of the starlight, right? So the star, that's how we even know they're there. We're looking at a star in the distance and suddenly it becomes a little tiny bit dimmer. And that means that something's passed in front of it. And if you see this happen sort of regularly and with an orbital period, you can sort of identify that it must be a planet orbiting around it. And as the starlight some of the starlight is blocked by the planet, but some of the starlight also just filters through its atmosphere. So Earth has an atmosphere, and that's what keeps us alive. It contains our oxygen, it contains the carbon dioxide and different things that we need, the plants need, and the oxygen we need. And that atmosphere is made up of lots of different elements. So we've got oxygen, nitrogen, carbon dioxide, methane, all those things. Different planets will have a different atmosphere containing different chemicals and different molecules. And the light can filter through that atmosphere. And depending what different molecules are in there, whether it's oxygen or hydrogen, they will interact with the light differently. So if sometimes oxygen will absorb certain wavelengths of light, and then when you look at that light, if there's some of those wavelengths are missing, you can say, that must be oxygen because it's missing that light. But then the issue that happens when we're doing that's called the atmospheric spectra. And the spectra, you sort of describe it almost like a signature of the planet. Every planet will have a special signature, which is their light spectra. But clouds can interfere with this spectra. Okay, so if you think about our clouds are only made of water, and they're white, they're very bright, so they're reflecting the light. And if light tries to pass through our clouds, they can be reflected off or they can be absorbed. But anyway, whatever they do, they're sort of interacting with the light differently than a clear atmosphere would. And clouds on other planets could be made up of anything you can think of. There could be a cloud. So for example, there's one planet that always stuck with me that's blue. So when you observe it, it's blue like Earth, but it's not blue because of water. It's blue because of this hazy atmosphere it has. And in its atmosphere, it actually has clouds that are made of glass. So on this planet, there's big storms that send this glass flying sideways. It's not Neptune, it's an exoplanet. So I think it's about 13 light years away. It's pretty far away, but it's got crazy clouds. And then, yeah, within our own solar system, we know that there's like Venus has sulfur clouds, and we know different things about the atmospheres within our own solar system. But anyway, sorry, get to this plot then. So this is a real plot used from a paper that I was looking at, and don't worry too much about exactly what this relative transit depth is. All I really want you to pay attention to is that each of these lines is a spectra for a planet, okay? And actually all of the lines except for this black line, so the light blue, the red, the orange, and this flat purple one, they're all the same planet, except we've changed the clouds. So we've imagined that this light blue line has no clouds, and this is what the spectra will look like for no clouds. But then the purple line is if we put loads of clouds around it, so really high altitude clouds covering the whole planet. And suddenly the spectra is really flat. It's completely different to that light blue line. So how can we even tell that's the same planet? We can't really, right? And then the other interesting thing is that the black line is a completely different planet. So if we look, you can see that the black line and the red line agree really closely, yeah? But the red line is one planet with some clouds, with patchy clouds. And the black line is a completely different planet with no clouds. But look at those spectra, they look identical. So when you looked at one of those, if you didn't know there was clouds there, you might think it was the black planet. But really, it could have been the red planet with some clouds. So the only point I'm trying to get across here is that the clouds are really changing the spectra of the planets that we see. So if we don't understand the clouds, we'd never really be able to figure out what planet we're looking at and what it could possibly be made of.
Do the clouds also change the like the signature, or could you just like find the correlation between each graph and then that correlation is kind of your answer?
So the clouds will change the spectra completely. And so the thing about correlation is a bit tricky because the clouds could be patchy, so they don't have to be the same the whole way around the planet. So depending on what side of the planet you're looking at, it could be a clear atmosphere, it could be a cloudy atmosphere. But the more important thing is to just know that clouds could form on that planet. And if they did form on that planet, what would they look like? Where would they form? Would they be really, really high? Because if they're high altitude clouds, and they're more likely to start reflecting light off before it even gets a chance to go into the atmosphere. Or are they really low clouds, kind of near the bottom of the atmosphere, where they might not actually make that much of a difference to what we're looking at? But it's a good question, because this is a big open-ended problem, because we just don't know that much. We're just trying, everything that we're trying to do is new. This is a really new field, because actually the first exoplanet was only detected in 1992, which I've realized for all you young people might sound really far away, but that was the year I was born, so that doesn't feel that far away. But over the number of exoplanets that they've discovered has effectively doubled every 28 months or something. So you can imagine the number. This is a graph. Start off with a few exoplanets, and now it's just getting bigger and bigger, and they're just discovering more every day. But they don't have very good models to understand what they're made of. Okay, so back to this old slide. Does anyone have any suggestions as what our assumptions might be and what our variables might be when we're trying to understand how a cloud could form?
I'd assume the same way that it forms on our planet.
So that is a very good first assumption, thinking about how things behave in our planet. And Isabella also said, so Isabella said the environment in the air, excellent, so that ties in. So the different atmosphere that we have. Environments in the air is also the pressure temperature profile. So if you think about a really warm day here, if we have a really hot day, are there usually many clouds? There's not, right? Usually the hot days are nice clear blue skies, and often cold days can be quite cloudy or rainy and miserable. And that's because clouds and things are only going to condense at a certain temperature. So the environment of the air is important to understand when a species, when I say species, I'm talking about oxygen or iron or all those different elements, when they might condense into a cloud. Sharanya said what the cloud is made of. That's hugely important because we want to know which elements are even going to become clouds, because each element interacts with light very differently, and they'll absorb light at different wavelengths, and that's going to interfere with our spectra. And Selene said what the clouds are made of and how reflective they are. Excellent. So the reflective thing is really important. You've tapped into a really important part, because once we know how these clouds form and the clouds are all there, that's great. But what does that mean? How do they reflect light? How do they absorb light? What's that going to do to the spectra that we see? Isabella said there is light to form clouds is an assumption. That's a good point. So if it's sometimes when the planet is rotating around a star, there's going to be a point where half of the, just like Earth, half of the planet is in darkness, right? Because it's on the other side of the star. So that you're not going to get very much information from that side of the planet at that point of the orbit. But by the time it gets around the other side, you might be able to see that bit, depending on how the planet spins. So that's important. Let's make sure I haven't missed any suggestions. Okay, so let me just throw some of the ones that we've been thinking about. So this simple microphysics is sort of the same thing that we've been saying throughout about the laws, the physical laws. So a lot of the first three that we mentioned were sort of all to do with fluids, whereas these simple microphysics laws are going to be like condensation. So when something is in vapor form and then it becomes a cloud particle, and evaporation is when it goes back to being vapor. You've got nucleation, which is kind of how something forms. If there's a little seed and then something nucleates onto it, kind of joins on and grows. And you have coagulation, which is the sticking together of two cloud particles. You could have a little cloud particle come together and form a big cloud particle. And those are going to interact with light very differently. What elements? That's exactly what Sharanya said, what the cloud's made of. So what elements might be present in that atmosphere that could possibly become a cloud? And we're also going to assume a well-mixed atmosphere. So we're going to assume that all of the elements are evenly distributed everywhere. So if you were going to get a water cloud, or you're going to get an iron cloud, that those things are kind of well mixed in the atmosphere and could form anywhere. It's not like all of your iron is up at the very top and all of your water is down at the very bottom. And then our variables, so we've got the temperature pressure profile, which is like as Isabella said, the environment. So how cold it is, where it's cold, where it's hot. The mixing efficiency, so that's kind of a more technical thing I'm getting into now, and that's how well the atmosphere mixes together. So it could be to do with winds, it could be to do with heat, how the convection, how things start to move around, but how well all your cloud particles are going to kind of mix together.
What about the reflective tendency of the possible magnetic field of the planet? That if it has a large magnetic field, then it could accidentally redirect light around. So even if it's totally clear, very little light may be reflected.
Yes, so that's even, at this point, we're not even thinking so much about the reflectivity of the clouds, we're just thinking about how they form. So once you have a better picture of how the clouds form and where they are, then you would start looking at the reflectivity, which is going to be the next slide. So just hold that thought. Okay, so then this next one is the sedimentation or the rain efficiency. So that's, we think about clouds and then our clouds form and then they rain and the clouds disappear because all of the clouds has turned into rain. So that's going to be an important process to think about. The size of the cloud particles is important, coming back to the idea of how they reflect light, and the number of particles is important, because again, how they reflect light and how they interact with each other. And I'm going to show you another real slide from a presentation actually in this bottom left, now that you're all learning Python, you could go and download this code. But this is actually a cloud code that we've been using and that NASA use called Virga. And this is just a simple slide to kind of explain how we model the cloud. So we start with our assumptions and our inputs, which I mentioned most of on the other page, on the other slide. And once we have those, we put them into our model, and there's two sort of main modeling steps. So the first one is that we need to figure out the amount of cloud material, so just the amount of it in the atmosphere. And the way we do that is that we solve an equation that looks at how well the particles mix together, how they diffuse in the atmosphere, but also how they rain out. Okay, so we solve, that's one of our when Jazz talked about the physical laws that define the problem, this equation that defines this mixing, this upward turbulent mixing and this downward rain, downward sedimentation. That's one of the laws that we would have to consider. And once we know how much material we have, we think then about how we can distribute that into some sort of particle size distribution. So we know we've got X amount, but how much of that are little tiny particles and how much of that are big, massive particles, because that's going to be very important when we're trying to understand how they reflect light. And then the final stage of that, so the output of the model are these three parameters, which is tying back into what Patrick was touching on, is how they reflect light. And how they reflect light, the clouds that is, so nothing to do with magnetic fields at this point, is defined by these three parameters. The single scattering albedo, so that's how likely it is that a particle would scatter light rather than just absorb it. You've got the asymmetry, which is, it tells you whether the light will be forward or will be scattered forward, or it could be scattered backwards, or it could be scattered over there or over there. It could be scattered anywhere. And the asymmetry parameter sort of describes that scattering. And then the optical depth is sort of telling you almost how thick that cloud is. If you've got a very high optical depth, I mean, you've got a really big, fluffy, thick cloud. And if you've got a low optical depth, it might mean that your cloud's quite spread out. You could almost see through it. And then we use all those things along with some other code, which is called the radiative transfer code. And that's how we would get out our atmospheric spectrum, which is the signatures that I was showing you before. So we use all of this stuff, different modeling steps, and it'll all come together to help us get this spectrum. Does anyone have any questions? This is quite a heavy slide of clouds.
I just wanted to mention that I think it's cool that here you have a graph of particle sizes, which was actually what you were tracking for your Blender project too. So it's just a good example of how you're modeling completely different things, how to make a smoothie versus how clouds form, and you end up with similar graphs at the end or similar outcomes that you're looking for.
Yeah, exactly. And actually you could, not something I've done, but one of the things we've thought about is if we can apply the same sort of math, the same sort of modeling of how particles get chopped and form that Blender's distribution, and think more about how particles come together, and that could be the coagulation thing that I talked about in clouds. It'd be sort of the reverse model, but it's all of the same sort of techniques, just in two very different applications. Okay, well, if there's no questions. Oh, we've got one more.
Oh, I deleted those slides actually. So those, I'll just mention now that it's up there. We also had a colleague who worked with us who helped to design cars to make them go faster, which is a lot of, so we talked about you can model the behavior of fluids, and actually air is also a fluid. So this is about modeling the behavior of air and how it interacts with a car. So actually we don't have a huge amount on this. It's just this very brief slide, I think, but basically, as before, we have to assume the airflow follows some simple rules, and we also have to have some constraints on the size and shape of the car. But this is really how they design aircraft and how they design cars, is they use mathematical modeling. They use these equations that are derived from physical laws, and they solve them for lots of different shapes and find out what's the best.
Okay, so we've just talked at you guys for about an hour, so we're going to give you a 5-minute break just to stretch your legs, and then we'll come back to finish off the end of the session.
Kiva, if there were no travel restrictions, where would you be? Which NASA location would you be at?
I would be in California at NASA Ames.
Mhm. One of the mathematicians we work with, he's a mathematician from Mathematics Association of America, James Tanton. His wife is, she's heading some big projects. She has international scientists working under her. Her name is Lindy Elkins Tanton.
Okay.
And he said that they were supposed to have a mission that she was in charge of, like in 2022, go from the Florida, the Port Canaveral, NASA.
Oh, really? Wow.
So yeah, but he's a really great guy. I know him. I don't know her.
Yeah. Wow. And so it's not she was supposed to, is it not happening because of COVID, or what's the?
I don't know. I mean, it's still, I haven't asked him, but he was here. He visited us. We were making a video here with the basketball team, and he was telling us that, oh, we'll be back here, in 2022.
Yeah. Wow.
She works, I think, in University of Arizona in their astronomy department, I think.
That's cool. Actually, Arizona, my boss has just left NASA to go head up the planetary science division at University of Arizona in Tucson.
Mm-hmm.
But that department's like a huge department, like one of the best in the country. So
Really? Yeah. I think she
yeah.
may be in Phoenix because he's always posting about his mountain climbs in Phoenix.
Oh,
Mountain
really?
climbs. Yeah. Can you share the presentation with Navdeep so that we can, or put it, I don't know if you can put it in the Google Classroom, like in the Drive.
Yeah, no problem.
Navdeep posts the video. Oh, I should have paused this. Let me pause the recording.
Microscopy work. I thought I'd just quickly show the video that wasn't playing in case anyone's interested, because I think it's quite cool because it's hard to sort of grasp. So let me make that full screen. So this is the image that the urologist will be looking at. So you can imagine there's a scope inside of a patient's kidney. I don't think this is particularly sort of gruesome by any means. You're seeing inside of a kidney, but obviously feel free to not look if it's something you don't want to see. But that's a kidney stone, and this is inside the patient's kidney, and that green light is the laser fiber that they end up firing to break the kidney into little pieces. And I think this is interesting because it shows why it's important that we have lots of fluid coming in to wash away these kidney stone particles. So that's the kidney stone there, and that green light is the laser fiber. And at a certain point, the urologist will start firing that laser fiber, and it's going to start breaking up the stone. Or the video will stop playing right at the exciting part. And you can sort of see that there's fluid flowing around. There's lots of little pieces of sort of stone particles and things washing around. But actually, once this laser fiber starts firing, which I think happens very soon. There you go. So you can see that they've started firing the laser and they're sort of breaking holes into this stone, but you can see it gets really hard for the urologist to see at a certain point because all these parts of the stone are clouding up the field of view of the camera. And that's when they need to get more saline solution flowing through to wash away the pieces. So that was just that video, in case anyone felt that they'd missed out by not seeing it. But I think if everyone's back now, we can probably segue into, we just have a short, basically, a short little sort of section now, and then quite soon.
Oh, another 5-minute break.
Oh yeah, sorry, this is just the last slide. Okay, right, so we're going to go back to Slido, but a slightly different code this time. So if you open it up and type in OMC models instead, you're going to be answering, how are these models similar or different to your plant model? So of what you've heard from us today, what are the main differences and similarities? Okay, we have to determine the factors like variables and assumptions. Very good. So you have to think a bit more about what to give your model. So you're, yeah.
Sorry, I didn't mean to cut you off. I was just going to say, yeah, because I guess in the plant model, you're basically given, there's a limited amount of information you have, right? You have that data sheet with sort of 4 factors. So those are going to be your inputs to the model.
Mm-hmm.
Great similarity. Yep. So in all of the models we looked at and the model you're working on, it's basically, it boils down to mathematical equations that are being used to solve the problems.
Yeah, we're not using any physical ideas in the plant model. And that's actually one of the main takeaways that we were hoping that you would get, is that there's different kinds of mathematical models you could be working on. So the ones that we presented were all very physical and based on industrial problems, where it's either manufacturing or optimizing some sort of process. And all of those things are very constrained by what the physics will let you do. There's only so much we can do that isn't being controlled by a physical law. Whereas the plant model, you've got a lot more flexibility of how you could allocate these funds. The only thing you're really restricted by is the amount of money you have.
Yep, somebody said they both demonstrate ways to accomplish tasks efficiently, which I think is great. That really, I think all of the problems we looked at, so we talked about redesigning a scope to make kidney stone removal more efficient, redesigning a blender to making a smoothie more efficient, redesigning an extruder to make cereal making more efficient, and then modeling clouds. I guess that's still to the task of identifying planets. You're still making that more efficient. So you're right, all of these have that in common. And then, of course, your project is looking at how to most efficiently allocate funds.
The must choose priorities is a really good point, because I think we mentioned in all of the models we talked about that there's a lot of different complexities, and you sort of have to start at a simple point. You start with a simple model and you start to build it up. So when you look, for example, my blenders model, we originally had thought it was going to be a lot of fluid dynamics and looking at how the fluid moves around the vessel, like Patrick was talking about. But actually, we realized that we could get a lot of information, and most of the particle size distribution was just being determined by the chopping. So without even thinking of really complicated fluid dynamics and just thinking of simple chopping, we got a pretty good model. And then we could have made it more complicated had we more time to add in all that fluid dynamics, and that would have just made it even better. But we had to prioritize which of those 2 sort of directions we were going to go in.
And there's a longer one that's come up here, so I'm going to read that out. So all of these models follow the same process, understanding the problem and determining variables and assumptions. However, these models are much more restrictive than the plant model, which gives much more creative freedom. I think that's a perfect summary of the differences, because yeah, basically all of these models, the starting step was to try and understand the physics, or as Kiva was just saying, to prioritize and choose which physics you're going to include and which you won't include. Whereas with the plant model, there isn't really that initial step, because you're basically determining your own new variable that's a combination of all these scores that you think will be the best way to allocate the funds.
Yes, I'm actually really interested to see what each of the group comes up with, because I bet you all are thinking about this in completely different ways, and you'll all have different ideas. So this is going to be a really good exercise to show the different ways you can model the same problem. Okay, so let's move on from this Slido. Okay, so we just did that.
And I think then we wrote
sorry.
down some similarities and differences that we just had off the top of our heads. And I think you've all captured these really similarities. They're all solving problems. We all have to have assumptions and variables. Although, as somebody mentioned, in the problems we talked about, we have to kind of figure out what those are. Whereas with the plant problem, it's sort of the variables are more given to you by the data that's available. And then differences, main differences, example we've shown are based on physical laws. So we're restricted in the equations that we can use. And exactly as you've all said, your plant model has much more freedom to create your own laws, which is quite fun.
Okay, so another group discussion is, what sort of laws are you making in your model? So if you go back to the Slido, it should be the same link. So you should hopefully just be able to refresh, or it should refresh automatically. What sort of laws are you thinking about in your model? What's restricting you when you're defining, when you're trying to model this plant funding problem?
And so when the laws are usually the things that end up becoming the equations.
Yes.
So sort of a law meaning how do the different variables relate to each other. So it might be interesting if people from different groups might share what sort of laws they're thinking about. Although maybe everyone's keeping their cards very close to their chest before right. before describing the models on Friday, which is fine too.
If my team's okay with it, I could share. One of our things that was pretty cool. Are you okay with it, guys, to share?
That's all right.
Okay. So we were doing, we decided on doing a expected benefit divided by cost in order to get a broad efficiency, a broad efficiency rating or number for our for each plant, and then ranking those plants by that rating. And we found this to be fairly successful.
That's great. Yeah, that's a perfect example of a law. So you're basically, your law is you're deciding how the cost and the benefit and the probability of success, how those will relate to each other. And there's lots. Yeah.
Well, there's already a law for it. It's just benefit divided by cost, or net benefit divided by net cost, technically. But so we just did that with the expected benefit calculated by just multiplying the probability by the benefit. And then so that's already a known law in statistics, investing, and betting even. And we did that and then just apply that to this project.
That's a great point, because there are other, I guess we're talking about physical laws, but you're right, you can be constrained by statistical modeling and probabilistic equations that are used. So there are other laws out there that can be applied.
Okay, we're going to move on from this because I think everybody would like to keep their secrets secret. So just before we finish, there's actually really only 5 minutes before you guys are going to get a break, but we thought about having a quick discussion in your groups. So in your own plant modeling groups, have a chat about this industrial problem that we're going to give to you. So if you imagine a company has come to you and they've said, we want a balloon blowing machine. We want a machine that's going to
probably
blow
already
up our
exists,
balloon.
but let's pretend it doesn't.
Probably
Yeah.
does. But this is a
Yeah.
really special balloon blowing machine because we want it to be able to do everything for us. So we want to be able to set the desired size of our balloon. And is there meant to be a balloon there?
There is meant to be a balloon, yeah.
The balloon is not there, but there should be a balloon in this gap. So you want to be able to say, this is how big I want the balloon to be. Machine, do your work. So they've come to you and asked, mathematicians, solve our problem, as so many people will do. So I want you to go into your, it's a bit of a hassle getting everyone into their breakout rooms, isn't it?
No, it's okay. Can everyone put the numbers of their group so it'll be easier for me to put you into the breakout rooms?
Okay, so then just before you guys go, it's going to be, what assumptions would you need to make for your model? What are your variables and what physical laws might you use? Now, I just want to emphasize that we're not asking you to write down a model right now. You've only got a couple of minutes. So just think about, same way we've done for the other problems, think about your assumptions, your variables, what the laws might be, what are the important things that your model would need if you were then going to go on to make it.
And then maybe one person from your group be ready to share those in just sort of a few seconds, less than a minute, really. Just give some of the ideas, summarize some of the ideas your group talked about when we come back. That would be great.
So maybe for this exercise, I can just do random groups since they don't need.
Yeah.
They can get to know other people.
That's a great idea.
Good idea.
Okay, so I'll do a random assignment. I'll split everyone up into 4 groups. Okay. All right, I'm opening the rooms.
Oh, I don't know.
Hello.
I think you put, do you want me to head back into that room? I don't know how I.
Whatever you want. Hold on. Let's see what some rooms had 2 people. So do you remember which room you were in?
I think it was 2.
Okay, so Alex is in 2, so you don't have.
Oh, okay.
Yeah, it's fine. So I think, is everyone, I guess, no, now people are coming back. Okay. I think we might have. Okay, they're closing in 8 seconds, so everyone will be forced out here. All right. Everyone is back.
Great. Okay. So did we just want to go around the different groups, Kiva, do you think, and ask if somebody wants to talk a little bit about what they thought?
Yep, sounds good. So actually the group I was just in, Celine was gonna give a quick overview. So maybe we could start with that group.
Perfect.
Okay, so some of the assumptions we made were that the balloons and the gas behave by the laws of physics and also possibly the ideal gas law. And also some of the variables are the kind of gas you're putting in the balloon. So like putting helium in could move the balloon around. So you could have something to hold it in place then. Also the different kind of balloon you're using, because some balloons have different elasticities, and that might affect the maximum volume of gas you can put in, the size of the machine nozzle, and the rate of air that goes into the balloon.
Awesome.
Excellent.
I like the thought too about if you have a helium balloon, it could move around and you might need something to constrain it, because that's something you wouldn't necessarily think about including in the model, but actually would be a really important design feature.
Yeah, it'd be kind of one of those things that once you do it experimentation, you'd realize your mistake.
You forgot that, yeah.
Okay, what about the next group? Is there somebody else that wants to give a quick anything different that they thought about, or if it's the same, that's fine.
So that was group 4. Oh, actually, we weren't split with those numbers, right? No.
Yeah, it was random.
We were basically just talking about like the materials we would use for like the machine, and also like the balloon and how that would like affect like the size, I guess, or like how it would kind of interact together. So
great.
Yeah, excellent points.
We were talking about the force at which the balloon is blown into, the properties of the balloon, and what the size of the balloon we were asked to blow up to. And we also talked about the type of the gas balloon.
Perfect.
I forgot to add, we also like talked about how we would pump the air inside the balloon. Like I think Ben was talking about like having compressed air and stuff. So we were trying to figure out like, how that would happen.
Yeah, that's actually such a good point. How the air, not just the rate of flow, but like what is the conditions of the air before it goes in, because that change in pressure could have a very big impact on whether the balloon, you know, shoots off the nozzle or how it fills up. So that's a very good point.
Yeah, and then there are different types of pumps too. So yeah, thinking about that, as you were saying, would be great.
Wait, I have a question about that. Do you mean like the reflexive property of compressing the air, that like if it's in a big container and then it goes through a small opening, that it might the gas might expand too fast inside the balloon? Is that kind of what you're saying?
Yeah, I think that's exactly what she was saying, because it's not just the total amount of air that you're putting in, it's also the speed that air is going at. And if you squish the air through a small tube, it's going to have to go at a faster speed than if you let it go through a larger opening.
I think there must have been one more group maybe that we haven't heard from yet. Was there 4 groups in total?
Yep, there were 4 groups.
And maybe the 4th group, maybe they're thinking that things have already been said, because it's often hard going last, which is fine too. Does somebody want to just mention, is that the case? Is the 4th group thinking that everything's already been said that they discussed?
Okay, that's okay.
Yeah, that's okay. Sure,
That's fine.
I think that was a great discussion anyway. You covered pretty much everything we could think about, so that was really good. So maybe then we're finishing a little bit late for your half-hour break, but will we finish now and then come back at about 15:15 to get on with your model work?
Yep, that's great. Thank you.
Perfect.
Excellent. Well done, everybody.
Thanks, everyone.
What time were we getting back at? 10:15?